You've got it rolling?
Yeah.
Okay, good. So this talk is about real-time analysis of MEG data. And what I'll do is I'll cover on various topics that have to do with real-time data analysis. I'm going to explain like general topics. I'll actually let me switch to the overview, to the outline slides. So I'll show the motivations. So like why would you want to do real-time analysis? And a very important aspect of doing real-time analysis of any type of data, of course, is having access to the data. Since it has to happen in real time, time is very important. But time is not all important, or at least it might not be as simple as thinking about making it as fast as possible. So I will explain the things you have to consider with regards to timing requirements. And then I will show a few examples which are slightly more technical and how you can think about doing the analysis in a way which makes it effective. Finally, I will tell a little bit about like the pipeline sequence, how to make an array of analysis working, and eventually how to close the loop. Because the whole point of doing real-time analysis is that you want to do something with the outcome of analysis in real time. Just analyzing the data in real time and not doing something with it is not a very efficient investment of your time, because that's also something that you can do offline. And again, here it is important to consider, as with one of the previous presentations, if there's no reason to make the experiment more complex than needs be, then don't make it more complex. So if you can run the analysis without doing real-time analysis, then run it without real-time analysis. But you can still do very fun things in real time, so that should not stop you from doing it in real time. Oh yeah, and then at the end I have some recommendations with regards to like overall efficiency of such a project. So the motivation. Closed loop systems allow us to interact with the subject's brain state. And the most obvious example of this, like the most mentioned example, is a brain-computer interface, where you would try to use a computer and a recording device that records brain activity to augment lost functionality of a patient. For example, a locked-in patient that is not able to control, doesn't have control over over muscles anymore. Allowing such a patient to communicate or to control, at least in a little bit, his environment is of course extremely valuable for those types of patients. Another domain where you can think about closed loop systems is if you present stimuli at a particular moment in time, depending on brain state, or actually maybe in this case depending on the phase of the heartbeat, which would be like one example of trying to stimulate really precisely timed, making the experiment efficient in terms of acquiring as much data as possible with very precise timing. So brain state dependent stimulation can be used to study the brain state, and it allows you to relate cortical activity to behavior. So rather than saying, well, I'm going to sort everything afterwards, what you can do is you can study the suboptimal or the optimal detection of stimuli. So if I present the stimulus when alpha is low, or if I present the stimulus when alpha is high, then that's something that we've done in NatMEG, and we know that the amount of alpha influences the chances of the subject perceiving the stimulus. So you better present it if the alpha is low than if the alpha is high. You can also use this to study plasticity and learning. So you can have an experiment in which a subject is trained on a specific task. Presenting stimuli at a specific moment in his brain state might make the training more efficient or less efficient. So this is really about using brain state dependent stimulus presentation to have a causal influence on the course of the experiment. So rather doing a correlation analysis afterwards, you can really cause the timing of the experiment to change, thereby really say that it's the stimulation, moment of the stimulation that caused the subject to learn or not to learn. So it allows for much stronger statements than with offline correlational analysis.
Robert, maybe a comment on this is that this could be also used in rehabilitation if you can invent a method to improve performance after a stroke, for example.
Yes. Yeah, so in brain-computer interfacing is often studied in the context of assistive technology, where assistive technology can be like for augmenting functions, but it can also be indeed in rehabilitation. And there's a lot of research going on in this direction. use on BCI, but I didn't want to very elaborately state that, because either you know it and then it doesn't make sense that I explain it, or you're not really interested in it, which means that I also should not spend too much words on it. But there's a lot of research going on in brain-computer interfacing, a lot of reasons why it's a very interesting and very hot research topic. Okay, but you might ask why. Okay, so MEG is like it's an expensive, it's a big device. You can't really move your head much, so it might not be the most practical tool for real-world BCI-based assistive technology. Well, the thing is, it has much better signal-to-noise for a lot of sources, especially for the superficial sources, than what EEG has. So what you can do is you can think of developing a BCI system with MEG, and then subsequently translate the knowledge that you have acquired with your MEG-based BCI system to the EEG case. And the EEG is cheap. You can use it in a home environment or a hospital environment relatively easily. So it's more about developing it with the best tools and then translating it into a practical system. The same thing can be told by changing MEG into fMRI. There's also people doing BCI using fMRI scanners. fMRI is also not really a very useful tool if you consider like having an MRI scanner at home or so. But near infrared spectroscopy might be might be sensitive to very equivalent signals as fMRI is. So maybe by developing it using fMRI and then using a NIRS device in a home setting, we might be able to make practical BCI systems. So that's why I think it makes sense to consider big scanners such as fMRI and MEG in developing BCI. Okay, accessing MEG data in real time. MEG acquisition software, actually, or in general, electrophysiological data acquisition software usually offers a low-level interface. The Electa software offers a low-level interface using shared memory, Unix-specific inter-process communication. That means that if you're a C programmer and if you know how inter-process communication works, you can access the data. But it does require C or C++ programming skills, and you really have to dig into these Electa programming libraries. That's okay if you have an engineering background or if you have an engineer that can help you with this, but it's not very efficient. So what we have done is we have realized that actually we have the same situation with a lot of different systems. So in Nijmegen we've been busy with brain-computer interfacing projects for the last 6 years, where different research groups were using different types of acquisition devices. So in Nijmegen we have a CTF scanner, but this is the NatMEG scanner. We have a Siemens MRI system. We use small mobile EEG devices. We have near-infrared spectroscopy for a couple of experiments. We have a high-density ECOG recording system. All of these systems somehow offer access to the data in real time. But the consequence, if we started using it like this, would be that for all the different projects we would be writing analysis software that would be device specific. And that is something that we consider to be very inefficient. So what we did is within the BrainGain project, which has recently ended quite successfully with really nice deliverables, we've developed a buffer. And that buffer is part of FieldTrip, so we refer to it as the FieldTrip buffer. But I should directly state it's not a MATLAB specific buffer. It's a low-level interface to all of these acquisition systems. And what it offers a unique interface, a uniform interface to the programming language that you want to use for accessing this data. An initial programming language that we targeted was MATLAB, because that's what we're familiar with in Nijmegen. The consequence of having a single interface is that the analysis side gets much simpler, because a lot of these signals have very similar characteristics. They all sample at different locations in time. Sometimes time is very slow and locations is very many, such as with the MRI scanner. And sometimes time is very fast and the number of locations is relatively low, such as with the ECOG. But in general, they all allow us to represent data in the same way, which means that if you learn how to work with one of these devices, you can translate that knowledge to one of the other devices. So FieldTrip provides a system-specific interface. So we have interfaces for many acquisition systems. And very rapidly, we also have been developing interfaces on the application side, not only for MATLAB, but also for simple online displaying and for other platforms such as BCI 2000, Python, Java, C, C++. So basically we have a wide range of choices that you can make on this side with respect to like what kind of platform you want to use, and a wide range of acquisition devices that you can use this platform on. The idea is that we want to stream data in a closed loop system. So we have a brain, we record data from it, and this is the focus of the filter buffer. So the filter buffer does not solve the whole closed loop system. For example, it does not solve the hardware specific parts, but it sits at this interface of the hardware and of the analysis software. The analysis software would be your responsibility, but having a consistent interface, of course, means that you can use expertise from other people that already have been developing analysis software. So that means that you can use a large library of analysis software that's available here. And also stimulus presentation and feeding it back to the real physical world. Well, that's not part of this project. But of course, there's a lot of expertise available there, what you can use. The implementation of the filter buffer consists of a ring buffer. So that means that a considerable amount of data is represented in a way that allows you to access the data. Making it available in the ring buffer relaxes the whole timing constraints. So rather than streaming data block by block from the acquisition software to the analysis software, what it does is it streams the data in a ring buffer, and the analysis software can get either the last snippet of data, but it can also slide over the data more in a leisurely fashion. So the analysis side decides when to pick up data when it considers that convenient, and it can also look back in time if needed. That relaxes the constraints on the analysis software, because what you normally would do is you would first have to start implementing the buffers in the analysis software. And as I already stated, the analysis software can be in a variety of different higher level programming languages such as MATLAB and Python. Okay, so in NatMEG we have a CTF MEG system. So one of the first devices that we targeted was a CTF scanner. But very quickly we started collaborating with other people. And this is a 2001 publication by Gustavo Sutra and colleagues who developed the same interface for their NeuroMag system. Like in the true spirit of open source collaboration, they shared their interface. They made it part of the filter package. So filter now has this interface for the Electa system. Of course, we've been trying it out here, and it just works, which is really nice. The design strategy for making real-time analysis works is that you start offline using data on disk. You can think of your file on disk as a buffer, and you can read from it. Once you have optimized your analysis such that if you read a second of data from disk, like the amount of data from disk that represents 1 second of real time, and if you can process it within 1 second, well, then you can start considering taking it online. Because if your offline analysis is so slow that it would not be able to keep up with real data streaming, it wouldn't make sense to try it in online. Starting offline really helps a lot because you can much more easily play with the data. Okay, so then you have it online, for example, using the NeuroMag MEG system. The nice thing is that subsequently you can also use the same software using a large variety of EEG systems. So translating it from the MEG lab into a different setting where EEG is being used is actually not very hard. The channel count will be different, the spatial characteristics of the channels will be different, so they will not be as focal as MEG channels, so you might have to use a different spatial filter, but the overall processing strategy would be exactly the same. And if you would want, you could also come to NatMEG and visit us and use it on our CTF MEG system, because it has exactly the same interface. Okay, so for those of you that are familiar with brain-computer interfacing, there are other platforms, and BCI 2000 has been around the longest as open source platform. It's a very large and a very successful project. I'm also helping Gerwin Schalk and colleagues out with the BCI 2000 platform by giving a hand at workshops and like in interfacing. It's really a nice project, but it's implemented in C++. The design of BCI 2000 is such that the data processing is done in filters. Like it's a stack of filters. Every filter processes the data in a particular way and then hands on the data to the next. It has an interface to MATLAB and Python, and it also has an interface from and to the filter buffer. So it's not necessary that you have to choose between either the filter buffer and BCI 2000. You can use both. Another large and successful platform has been developing over the last, I would say, 5 years or so, mainly in France, is OpenVibe. Again, it's implemented in C++. It has a very technically skilled developer group behind it. It has a graphical user interface with building blocks. So you basically drag a block and you pull arrows. It also has an interface to MATLAB and to Python, and it again has an interface to the filter buffer. So it's not about making a choice for either one or the other. You can explore both, or you can explore all three of them, and you can make your choice which is the most appropriate tool for getting your research done. If I compare the filter buffer to the other platforms, then BCI 2000 and OpenVibe are more tailored to the experimental end user. Extending them requires more significant engineering expertise because of them being like primarily implemented in C++. So I see a lot of people that start with BCI 2000 and then start implementing their own real-time analysis platform in C++, and then they leave the lab and then the platform is never used anymore. So I think that's a bit of a pity. It's just C++ is more challenging to work with, and it's more difficult to pass knowledge that is built in such a low-level language onto like people in your experimental environment. The filter buffer approach is more tailored towards rapid application development. Like the development is faster. It might not be computationally as efficient, so it might not be something that you're going to integrate into a real-world, like home appliance type of thing, Raspberry Pi or an Arduino. It's too heavy for that. But you can do your experiments with it very rapidly. And I think it's easier to extend your expertise that you have or that you're currently building up in terms of offline analysis to the online analysis case, because it uses like existing MATLAB interface, so you can use a lot of filter functions in your real-time experiments. So what I now plan to do is give a short demonstration for how the filter buffer works. So for that, let me switch to mirroring. Oh yeah, so let me first explain what it consists of. So what I'm going to do, because I'll now switch out of presentation and I'll have to mess around a little bit with the computer. What I'm going to do is I'm going to start 3 programs. I'm going to start a sine wave generator, which is going to like generate simulated data. I'm going to start the filter buffer. Well, the filter buffer is not something that you can really see, but I'm going to open a terminal, and within the terminal I will start the filter buffer application. This is a TCP server. The sine wave generator will use a TCP connection to write data to the filter buffer on the same computer. And then I'm going to start a buffer viewer who's going to connect here and read the data. Once I have this set up, once you can see that the data is streaming from here to there, I will connect also with MATLAB so that you can see how the MATLAB interface looks like. Okay, so this is my terminal. So what I'm going to do is I'm going to go to the filter directory, and where in real time there's a bunch of directories. In the bin directory, there's binaries that are compiled for various platforms. Like for us, it's really important that we can run this on different types of computers. Our acquisition computer is Linux. We do a lot of the analysis on Macs, but also a lot of the analysis on Linux. We're trying out certain things on Raspberry Pis, which are like these really small computers that you can easily build into a project. And of course, Windows is also one of the platforms that we targeted. So let me go to this directory, and you see a bunch of applications. The ones that I'm going to start are the sine2ft, which is a sine wave generator. Then I'm going to start the buffer viewer, which I'll put here. And then over here I'm going to start the buffer itself. Okay, so what you see is that in this window I have the filter buffer, and it's sitting there, it's listening, it's waiting for data to come in. Here I could specify, so this is just one example application, of course. This is normally this is the MEG scanner, but this example program allows me to specify where the data has to be written to, on which port, like on which TCP port, and some characteristics of the data. So the number of channels, the block size, and the sampling frequency. So in this case, the 2,000 samples per second will be generated for 16 channels, and like approximately 4 times per second, the data will be written to the filter buffer. So it has now connected. So data is now streaming from here to here. This program again allows me to connect to a buffer, and what it will do is we'll just read the characteristics of the data and it's going to display it. So if I connect, then what you see is data streaming from here to there, and data streaming from there to there. This program is constantly checking, like, is there new data here? If so, get the data and plot it. Okay, so what I can do is I can use this slider, like to speed up or slow down the oscillations, or use the amplitude slider to make them smaller or larger. Okay. What I've done now is I've simulated data with a relatively coarse block size, and that is something that I'll come to later in the presentation. But if I now like make this block size a bit smaller, so for example 200, what you see is that it runs smoother, because this one is now able, the viewer is now able to get the data from the buffer 10 times a second rather than 4 times a second. Yeah? Let me now connect to it from MATLAB. So I've prepared a small script to help me quickly going through it. Yes, so this is from us playing around yesterday evening. So the file name that I'm now specifying is actually, it's a URL. So it's not a file, but what I'm going to do is I'm going to do the same thing as what you've been doing over the last 2 days. I'm going to read the header from this buffer. So header is ft read header from this file. So what you see is 2000 Hz sampling rate, 16 channels. There's a number of samples and some other details. If I read it again, let me move it up a little bit. What you see is that the number of samples has increased. So whenever I read it, the number of samples increases. So I'm abstracting away that it's a ring buffer. So not all of those samples might be accessible anymore. Like in general, you should count on about 5 minutes of data being in a ring buffer. But you can think about it as like a constantly growing file on disk, except that you can access this one much faster.
On memory.
Yeah. So this is not. So this is like a file on disk, but you can access it much faster because it's in memory, and you can access it from an arbitrary computer because it's a network transparent interface. So what I can let me run this piece of code. So what's now happening is that in an infinite while loop, I'm just reading the header and I'm just showing it. And what you see every time the header is shows that the number of sample increases with 200, right? And that's of course something that I can use with such a piece of code. So what I'm going to do is I'm going to execute this code, so that's an infinite while loop. So while I don't press Control C, I'm reading the header, I'm determining the beginning sample, the end sample, and I read a piece of data from the begin to the end sample. The end sample is header end sample, so it's the latest sample that's in the buffer. The begin sample is the end sample minus 1 second of data. So what I'm doing here is I'm reading the last 1 second of data. I just use standard MATLAB plot function to plot it with along the horizontal axis a sample number. I make the axis tight and I call draw now, which forces MATLAB to update the figure. And then I'm just showing where we are in terms of sample numbers. Oh, I forgot one line, I think. So what you now see is that it's plotting 16 channels, 1 second of data, like sliding window. You're only seeing one channel because all of the channels have the same sine wave in it. Of course, you can now imagine changing the code such that you do something smart with the data rather than plotting it. MATLAB plotting is not particularly fast, but it works, and it serves the point of showing that it works.
The number of samples it's showing?
Actually, let me see what it's showing there.
But you could easily make like a TFR and plot a TFR or something like that.
Yeah. So what it's showing, it's the end sample, like the latest end sample minus the previous end sample. So it's how many samples have passed since the last time that it showed it. So what you see is that it updates slightly faster than once every second. Alex?
So, basically yesterday at 11:30, Robert told me it would be really cool if you managed to get the buffer to work in Python over the Wi-Fi network tomorrow. And I said, just give me 5 minutes. And he says, I think I need to go to bed and you will do it afterwards. He was right because it took me maybe an hour and a half. But it's surprisingly, now it works. So if you look at my screen, you see something that's not really sine wave because it's just a proof of concept. But if you play with the slider, you should see that the
Yeah. So what?
You could in principle just hook up onto the MEG system. I press start,
Yeah.
and you can display the MEG data here as well.
Yeah. Yeah. So what we're now doing is.
Should you tell me at midnight?
So the purpose of this demonstration is that it's really not that difficult to use a different programming language and a different computer for the analysis. Of course, Wi-Fi would not be the ideal network connection to do it fast, but like there's a lot of overhead in getting the data from here to there, and there might be jitter, like maybe 100 or 200 millisecond jitter or so. But the most important is that it's quite easy to do.
That's what I was just about to ask. That if you want to do brain state dependent, like stimulation or task, it should be really fast.
Yeah.
How fast can you go? What's the buffer size?
Good question. I will come to that. Okay. Okay. So let me close the various things. Also stop this one. Okay, so timer requirements, because that's really like, is it fast enough? If we think about real-time analysis, we tend to think about real-time as like instantaneous. But like computers are never instantaneous. Computers are very fast, but they're not instantaneous. More important to think about the requirements here are not that it has to be instantaneous or very fast, but it has to be very well controlled. Because if you know that you have with a fixed delay that you can analyze the data, then you can compensate for the delay. So if you want to address timing requirements, it's more about like quantifying the timing requirements. And we have delay. So if we look at this like simple linear model, we have the delay y, which is a function of the amount of data that has to be like passed through the system, passed through the interface or passed through the processing pipeline. So this is the amount of data, and then we have the speed of the operation, and we have a certain offset. However, the total delay that we have to deal with is the delay plus a certain amount of jitter. So it's not only about the bandwidth times the data size plus this offset, but it's also about this jitter. And that would be that's why it would be a very bad choice to do this over Wi-Fi, because there would be a lot of jitter. So if you're thinking about quantifying time, if you're able to quantify how fast you can run the analysis, but then you would be able to compensate for the shift. For example, if you know that you're always 100 milliseconds behind, then you could try to predict like the next cycle in the alpha oscillation in which you want to present the stimulus. Or if you're looking at like heart rate dependent stimulation, you can detect the heart rate. You can detect where you are in the heart rate and then stimulate after the subsequent heartbeat. So that's something that you can compensate for. The jitter is more difficult to compensate for. And so understanding the causes for the jitter helps in getting the timing requirements really tight. So minimizing delay means like where you can think about reducing the data size. Don't process data that you don't need. You can of course think about increasing the speed of your algorithm. You can increase the bandwidth of your transfer. So rather than using a Wi-Fi connection provided by the university, we could have used a switch. And then using a gigabit switch would be faster than using a 100 megabit switch. But minimizing jitter is a little bit more challenging. So let me explain one of the reasons why we have jitter. So what I'm showing here is a window in which I want to analyze data. If the data comes in and fills this window of data, I can process it and send the result of the processing away. The next piece of data arrives, I process it and I send it away. However, in the analysis what we often have is we have a certain window of data, and then we have an acquisition system. An acquisition system is making data available with a certain block size. And that block size might be like this, which means that I don't have enough data yet for my algorithm to work. So I have to wait for another block. So I take this piece of data, I process it, and I send it away. So I close the loop with it. This piece of data, I have to put it here, because I still want to process it. Then I have to wait for another piece of data and have to wait for another piece of data. And then I can, again, process it. So the problem is that at the time that I'm processing it, time has already passed considerably. Not only considerably, here I'm processing it like this amount of time too late. Here I'm processing it this amount of time too late. So what happens if the block sizes of the processing do not match with the block sizes of how the data is being made available? I'm going to get jitter. Also, if the block sizes are too long, so if you try to make it faster by processing smaller blocks, you're still going to get jitter. Because this part will be processed, but only once this part is available from the acquisition system. So I copy it over there, and I again have to wait, and I again have jitter. Is this clear? Okay. So understanding jitter is important, because that influences how accurate you can get the timing right. Data is processed in blocks everywhere. The amplifier processes data in blocks. The USB port, which is quite often with EG systems, are used for copying data from the amplifier to the acquisition software, is processing in blocks, or the networking TCP package is processing blocks, and the processing steps that you're implementing is processing data in blocks. So there's block sizes everywhere. And everywhere where there's a mismatch between those block sizes, you're going to get jitter. So unequal block sizes cause jitter. So although it's with the filter buffer, it's very easy to access the data, and it's very easy because it represents a ring buffer to work with arbitrary block sizes. Understanding the block size, if it's while it's passing through the system, still helps in making the timing of the system more accurate and in reducing jitter. Okay, so a question that I often get asked in this, like, okay, if we want to make it system faster, why would we work with block size? Why do we not process data always in one sample? And why do amplifiers not process data in one sample, and network interfaces, etc.? So if we consider this formula again, we have the delay, which is a speed times the data size plus some offset. That's for one sample. And if I'm going to send this data over a network, for example, and I have n one sample blocks, what I'm getting is I'm getting the delay, which is n times this one, which is n times the speed times the data size, plus n times the offset. If I send this data rather as as an n sample block over the network, I only have the offset once. So that means that processing data in blocks is often more efficient. It's often faster because the offset at a certain point is going to kill all the transfer. So that's why a lot of computing systems process data in blocks rather than one sample at a time. Okay. Well, what do we need for efficient analysis? Efficient is if it computes in well-defined time. That means that during the course of the experiment, time should not increase. And what I'm going to show as an example is running mean. So it's just an idea of how you have to think about doing the analysis. So I hope you can read the text. So what I do is I have an infinite while loop. But rather than plotting the data, what I'm doing is I'm reading the header. If there's no new samples, then I continue. So I just repeat. But if there's new samples, what I do is I read I read all the data, I compute the mean over the samples, and I update n, which is needed here. This is a very inefficient implementation because what I'm doing is here I'm reading all the data, which means that it's going to be fast at the beginning of the experiment. But if the experiment progresses, the amount of data that has to be transferred, the amount of things that have to be done in this computation increase, which means that it's linearly going to slow down. So that's not smart. So rather than doing this, much more efficient is if I keep a running mean, actually a running sum. So I initialize a vector that computes this, that holds the sum, and here I only read the data that I have not seen yet, so from the previous sample up to the current sample, and here I add it to the sum. Again I update n, and here I compute the average. So this is computing with constant time. So this can just keep running, and it's not going to slow down in any way. I can also do some other interesting stuff. For example, I can compute the variance. So rather than computing the variance by like taking all the data points and putting that in the MATLAB var function, what I'm doing is I'm keeping track of the sum of squares, and it allows me to compute variance. Which also means that I can compute a running z-score, for example. And a running z-score is of course interesting if I want to use some sort of a statistically motivated threshold. So this is just an example of how to think of a function that does not increase in time if it runs longer. So efficient is if it computes in well-defined time. Time should not increase. You should think about it using short amount of data. And this is more natural with streaming data. And you should, in general, think about like algorithms that increment something rather than algorithms that do a lot of stuff on each iteration. So potentially problematic are algorithms that have an unknown convergence time. So one of the things that we're doing in real time is do a head localization position. The MEG uses these head localizer coils, which are magnetic dipoles. We measure the helmet topography, and we can do a real-time dipole fit for each of the magnetic dipoles. That works quite robustly. The only problem is that this nonlinear optimization procedure, which will be explained tomorrow, has an unknown time in which it converges. So there's no guarantee that it can be done in real time. The thing is with a real-time head localizer, we don't care if it occasionally skips a piece of data. So we just always jump to the last piece of data and we perform the head localization and win the visualization. So, but that's just something that you have to keep in mind, that some algorithms have unknown or unspecified timing characteristics. Another aspect that you have to consider in timing is making it computationally efficient by combining linear operations on the data. So what I'm going to do is I'm going to show a spectral power estimate of a spatial filter output. Spatial filtering such as SSP can be used to like zoom in on a particular source of interest. And of course spectral power is, because spectral power is interesting, right? So this is an example. Here I'm taking a spatial filter, which is an n by n unmixing matrix. Could also be like an ICA based unmixing matrix. I read data, I determine sample 1, sample 2. I read the header, define sample 1, sample 2. I read the data. And then here, on this line, I'm multiplying my spatial filter with data, and then I compute the Fourier transform. So I have my spectral representation. Then I select the component of interest, and then I select the frequency of interest. So this is like a complex spectrum, complex Fourier spectrum. So I subsequently here I take the square of it to get the power estimate. So this is a very inefficient computation because in the end I'm only interested in one component, one frequency. So the different ways that I have to make this more efficient is by moving this spatial filter out of the fast Fourier transform, or by taking only the spatial component that I'm interested in and multiplying that with the transform. So this is going to make the matrix computation much faster. Or what I can do is just, rather than taking a fast Fourier transform here, I know that I'm only interested in a single frequency. So I explained this morning that a fast Fourier transform is very similar to linear regression. So what I can do is I could just give my regressors here, and I can do a GLM here on the fly, just computing a discrete Fourier transform. So this is really much faster than the previous implementation. Like, depending on the number of channels and the number of frequencies, like sampling frequency, it can be like 1,000 times faster. The fast Fourier transform, like the computational complexity of it is on the order of n times log n. So depending on the number of samples that I have, depending on the block size, it's going to increase not quadratically, but it's going to increase considerably. So the initial algorithm would not work for long sliding windows. Whereas the discrete Fourier transform that I'm using here is just has a computational cost which is in the order of the number of samples. So if I use this on a data segment that's twice as long, it's just going to take twice as much CPU time. That's something that I can deal with. Yeah. So and then there's some low-level aspects that you have to consider. So what I have is this is one way that I can do the computation. So I make the selection of W actually outside of the for loop. But then there's two options. Either I'm multiplying 3 matrices. So either I first multiply these 2 matrices and then that one, or I first multiply these 2 matrices and then that one. Let me think of and then depending on the number of channels that you have and the number of time points, one of them is going to be faster. So even thinking about how you put the brackets in your equation is going to make it faster. And this might be a level of detail that's not really relevant for you. Like if it's fast enough, then just use it. Okay? But this is just some tricks that you can exploit in making computation run really fast. Okay, so algorithm for efficient analysis. So with spectral analysis, you should not convolve. Convolving is slow. Better is to use a fast Fourier transform, but even better is to use a discrete Fourier transform. You can think about, I want to use multi-tapering, and for multi-tapering I have to use a fast Fourier transform. You could also use a Welsh approximation. It's not going to be as properly tuned as a multi-tapered spectral estimate, but still you can implement smoothing with the Welsh method, and it's computationally much faster. Even faster is to use autoregressive models. Just some ideas like to get you started with making things run really fast. You can use it might be interesting to look at external regressors. So you can do regression or general linear estimation. That requires the inverse of a covariance matrix. So what I can do is I can update this covariance matrix whenever a new block of data comes in, and then I can invert it. Computing the inverse is an expensive operation. So rather than computing the inverse in every iteration, what I can do is I can use an incremental small rank adjustment to the inverse of the covariance matrix, which is computationally much faster. So there's computational tricks that you can exploit to make it really fast. So in designing a pipeline, so the idea is that you start with data and then you do multiple analysis steps on it, producing an output result which is going to have consequences in the real world. For example, presenting a stimulus or controlling a wheelchair or a spelling device. So we have different building blocks. We have linear algebra with matrices and vectors. You have nonlinear operations. And the idea is that you take all of those and you combine them in a pipeline that transforms data from one form to another form. So this is how a pipeline, for example, might look like, where at the end you have transformed the data into a control signal. And with the control signal, you want to control the real world. So that means that, here you start with many numbers, like many data numbers. Here at the end, you have one number left, like one number which is send trigger, zap. So basically what you can think of is that this pipeline is reducing your data into one number, and that number is basically doing the thing that has to be done at a specific time. So that brings me to closing the loop. So raw data comes in and the control signal goes out. There might also be external events. So for example, stimuli are simultaneously presented or stimuli have to be updated. One example of that is the P300 speller, which I think is familiar to those of you who have like some BCI experience. The P300 speller is based on it's an assisted technology that's based on the P300, which is that if you attend to a stimulus and the stimulus appears, you're going to get a larger P300 than if you were not attending to the stimulus. So the subject is instructed to pay attention to the letter he wants to select. For example, well, let's say the P, and then in random order, the rows and the columns of this matrix are flashing, and the flashing is really rapid. So and it's in random order. So whenever the row or the column is flashed of the letter that he's attending, there will be a P300. So that's typically one where there's a lot of external triggers are being used, and then you have to detect the P300 in real time. And if you are sufficiently confident that that you have a P300 for one of the row and column combinations, well, that's then the letter that's selected. For closing the recipe, there's not really a general recipe. Like it really depends on whether you have one or multiple computers. It depends on the operating system and also depends on hardware capabilities. Sometimes you have a device that you can connect to with a parallel port cable, sometimes a serial port cable, sometimes with network, sometimes you need a BNC connection or so. But between computers we have like these options and Ethernet, and within computers we have single multi-threaded applications, so we can use shared memory, for example. So there's many options possible here, but it really depends on the application that you're trying to build. Well, yeah, you could also use TCP sockets. In terms of platform consideration, well, we have a low-level programming environment, and C and C++ are really fast. But they're very slow during the development. Debugging is difficult. Learning these low-level programming languages takes a lot of time. We have Python or Java or C#, which are slightly higher level programming languages. And then we have MATLAB, which I consider the most user-friendly in this family. This is where you spend least time implementing. This is also like the most inefficient code. Like Python is going to run faster, but probably you're going to need a little bit more time to implement in Python than in MATLAB, depending on what your background is. So what you have to consider is it fast during development? And is it fast enough during execution? The goal is not to make an infinitely fast real-time system. The goal is to make a real-time system that's fast enough. And to make it...
if you compile it.
MATLAB would not be faster if you compile it. there is the MATLAB coder toolbox, which translates MATLAB code into proper C code and then compiles it. That will make it faster. But the MATLAB compiler itself is just a pseudo compiler that scrambles the M files and that allows you to run it on another computer where you don't have a MATLAB license. So, but it does make it faster. So what you have to consider in choosing your platform for doing real-time experiments is mainly your own skills and in your own salary. And do you really want to implement everything yourself? Of course, that's interesting. Like it means that you will build up expertise for all the aspects. So, and especially for people with an engineering background, these are very interesting projects to work on. But if you take a slightly more macroscopic view, you also have to consider maintenance and support. Like if you build a system and if your lab starts depending on it, then you are also responsible for maintaining the system and making sure that new people can start using the system. And what if you leave? Like, will the system still be used? So long-term investments are also important. So looking at the different platforms, I would say, well, BCI 2000 and OpenVibe are really nice platforms if you want to use them off the shelf. If you consider and they're really better than Filter together with MATLAB. However, if you want to extend them, it's your consideration, but probably it's going to be faster if you use the filter buffer. And then on the language side with which you can develop, well, of course, if you're a Visual C programmer or a C++ programmer using GCC, that's fine, and these are like perfectly appropriate tools. I personally have a preference for doing things on MATLAB. Some other people might prefer Java or Python. But it's really, you have different choices and just pick the one which is most efficient for you. Because time is the limiting factor, but it's not necessarily the CPU time that's the limiting factor. It's your time that's the limiting factor. Because you easily spend a lot of time implementing such a system to find out that the brain doesn't work as you had expected, and then you're basically left empty-handed. Like you have a nice system, but you don't have any scientific results to show. So I think rapid application development is really something that you have to take serious. Rather than building everything up from scratch, you should just use the tools that are available and try it out. And then maybe the brain is doing what you had expected, but maybe it's not, and then you have to like redesign the whole experiment. So this is basically what you have to keep in mind. So to summarize, I touched upon the motivation, how to access the data. I dealt with like timing requirements, both in terms of jitter and offsets. Mentioned some algorithm for efficient analysis and how you combine algorithms in a pipeline sequence to make it run sufficiently fast. And then I shortly touched upon like how to close the loop, for which I do not have a general recipe, and efficiency considerations, which are mainly efficiency of your time rather than of the computer's time. Okay, that's it. Thanks.